Hey everyone, welcome to this explainer. Today we're embarking on a fascinating journey to solve one of the ultimate geological mysteries. What exactly is inside our planet? It's a question that's honestly puzzled humanity for centuries. Today we're going to look at exactly how scientists managed to crack this case without ever actually seeing the evidence with their own eyes.
You know, to really understand our planet, we'd love to just cut a physical plug right out of it to see what's inside. Think of it like buying a watermelon at the summer market. You might cut a small triangle out just to check if it's ripe and red before you commit. But when it comes to the Earth, physical limitations make that completely impossible. The intense heat, the crushing pressure, the sheer scale of the rock beneath our feet, it all stops us right in our tracks.
In fact, the absolute deepest hole humans have ever managed to drill, the famous Kola Peninsula borehole over in Russia, only goes down about 12 kilometers. And it literally took decades of intense engineering just to achieve that. For humans physically traveling underground in places like the incredibly deep gold mines of South Africa, we've only ever descended about 3 to 4 kilometers. Now, keep that 12-kilometer drilling record in your head for a second. When you compare that measly 12 kilometers to the Earth's massive 6,371-kilometer radius down to the core, you realize we've barely even scratched the surface. We haven't even pierced the skin of the apple, so to speak.
Since we simply cannot dig our way down, we've got to play scientific detective. So in this explainer, we'll cover the mystery of Earth's interior, look at clues like temperature and density, check out how seismic waves act as Earth's X-ray, break down the chemical composition, and finally piece together the modern structure of the Earth. Starting off with Part 1, the mystery of Earth's interior. If we can't go down, the information literally has to come up to us. Which brings us right to Part 2, our first big set of clues, temperature and density. As we go deeper into the Earth, these physical properties undergo some pretty dramatic transformations. Notice just how insanely fast the heat ramps up. For every 32 meters you descend, the temperature jumps by a full degree Celsius. By the time you're 100 kilometers down, it hits a staggering 1,200 degrees. And down at the inner core, we are talking roughly 6,000 degrees Celsius. It is an absolute furnace down there, driven by immense pressure and decaying radioactive elements. And right alongside temperature, we have density. The Earth's overall average density is about 5.5 grams per cubic centimeter. The surface crust that we're standing on right now, it's actually pretty light, hovering around 2.7 to 3.0. Yet down at the core, that number skyrockets up to 13.5. This proves unequivocally that the deepest parts of our planet are crammed with some incredibly heavy, tightly compressed materials.
All right, moving to Part 3, seismic waves, which act as Earth's X-ray. When the Earth violently shifts during an earthquake, it sends out massive ripples of energy that let us peer inside.
This illustrates the absolute game-changing difference between the two main types of body waves. We've got primary, or P waves, which are super fast and can travel through solids, liquids, gases, you name it. But then we have secondary, or S waves. They're a bit slower, but here is the magic detail. S waves simply cannot travel through liquids. They completely vanish. This one quirk of physics becomes the ultimate clue to mapping the Earth's innards. Because S waves get stopped dead in their tracks by liquid, whenever an earthquake happens on one side of the planet, they create these massive shadow zones on the opposite side. This S-wave shadow zone stretches across roughly 40% of the Earth. If the Earth was totally solid all the way through, the waves would just reach the other side. Because they don't, this definitively proves that a massive molten liquid barrier exists deep inside our planet.
Next up is Part 4, chemical composition. Armed with those huge seismic revelations, let's look at how scientists historically categorize these layers based on their chemistry.
A scientist named Edward Suess originally proposed this brilliant three-layer chemical model. He categorized the top layer as Sial, made of lighter silica and aluminum, which forms our granitic continental crust. Underneath that is Sima, heavier silica and magnesium forming the basaltic ocean floors. And right at the center is Knife, nickel and iron. These are the super heavy metals that literally sank to the core during the Earth's formation. It's basically a giant planetary settling tank where lighter stuff floats and heavy stuff sinks.
But let's just zoom in on that outermost crust for a second. It is honestly mind-blowing to realize that the solid ground we walk on, the dirt and rocks beneath our feet, is actually composed of almost 50% oxygen. 46% of the crust is oxygen, bound up with 28% silicon and 8% aluminum. It really shifts your perspective on what solid rock actually is, doesn't it?
Finally, let's wrap this all up in Part 5, the modern structure of the Earth. Let's assemble all our seismic X-rays, our temperature clues, and our chemical data. We live on the crust, an incredibly thin layer averaging just 35 kilometers deep, representing a mere 1% of the Earth's total volume. This superfragile crust basically floats above the massive, dense mantle, which goes all the way down to 2,900 kilometers and makes up a whopping 83% of the planet's volume. And nestled right within the upper mantle is the asthenosphere, a highly heated, slushy, molten layer filled with radioactive elements, which happens to be exactly where volcanic magma is born.
Below that mighty mantle is the core, making up the last 16% of the Earth's volume. The outer core is liquid, and we know that for an absolute fact thanks to our disappearing S-waves. But the inner core is a totally different story. Even though the temperature is a blazing 6,000 degrees Celsius, the weight of the entire planet presses down on it so hard that the iron and nickel are squeezed into a dense, completely solid state by unimaginable pressure.
Now, as seismic waves move between these very different structural layers, jumping from solid to slushy or solid to liquid, they suddenly jump in speed and bend at boundary lines we call discontinuities. To keep track of these invisible borders, geologists use a pretty handy little memory trick. Ko, mo, ri, gu, le.
Let's decode that real quick and build our complete map. First, the Conrad boundary divides the upper and lower crust. Moving down, the Mohrvisic separates the crust from the mantle. Next, Repeti divides the upper and lower mantle. Further down, Gutenberg marks the massive shift from the mantle into the liquid outer core. And finally, Lehmann is the boundary between the liquid outer core and the solid inner core. Those 5 names mark the exact depths where the Earth's density radically and suddenly changes.
And that brings us to our final thought. The fact that scientists have mapped out these boundaries, identifying a 6,000-degree liquid iron ocean buried thousands of kilometers beneath our feet using nothing but the echoes of earthquakes and the principles of physics, it's just brilliant. It is an incredible testament to scientific deduction, and it really leaves you wondering, if we can figure out exactly what's happening thousands of kilometers below us without ever digging a hole, what other impossible mysteries in the universe are just waiting for the right clues to be uncovered? Keep that curiosity alive, and thanks so much for joining me on this Explainer.